All right, babies, here we are at the end of chapter 10, and we're looking at 10:7 and geometric sequences. Let's go back. Do you remember what a sequence is? It's kind of like, a really cool list of numbers that you see a pattern. You've been dealing with those for a long time. And so we might have one, two, let me think, one, two. It's one of those days. 1, 2, 4, 8. And you can tell what I'm doing. I'm kind of doubling every time, right? 4 plus 4 is 8. 8 plus 8 is 16. You know about Fibonacci sequence. We had a problem with that where you've got 1. I think we started off with 0, then 1 again. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. These are all beautiful sequences. We also studied in depth arithmetic sequences where each next value is just an addition of the same value, and we called it the common difference. Remember that way back when? I don't remember what chapter it was. 4, right? We were in chapter 4. That happened. So you might start off with 3, and then you might get, I don't know, let me try something nice. Let's add a -2. So then you get 1, add another -2, you get -1, add another -2, you get negative, anybody know, -3, add another -2, -5, and you can see the process. So this one is called arithmetic. This is a fancy one, it's Fibonacci. And this one here is called a geometric. And we'll talk about the quality that lets you know you're dealing with a geometric series. So a geometric series, the idea of a sequence. Series is a different thing. Sorry if I was saying series. Sequence. A geometric sequence is a sequence such that each number before is a common multiple of the other one. So let's see what I'm talking about. So let's say I have the number 4. I start off my sequence with the number 4, and I'm going to, I don't know, multiply each subsequent number by 1/2. So 4 times a half is 2, 2 times a half is 1, 1 times a half is 1/2, 1/2 times 1/2 is 1/4. This would be considered a geometric sequence. In fact, let's do another series like that so we can kind of get a feel for what it is. So I don't know, let's start off with like a -2, and let me multiply each consecutive number by, I don't know, 3. Let's do 3. So, or a matter of fact, let's make it fancy, -3. So -2 times -3 is going to be a +6. +6 times -3 is going to be a -18. +18 times -3 is going to be a +54. A +54 times a -3 is going to be, I need to do that multiplication. It's going to be negative. I'm going to get 2 down there, carry 1, 3 times 15, 16, 162, and we can continue so forth and so on. So when we talk about these values, you remember it with sequences, we kind of talk about each one as a term. So this would be the first term. We would call it a sub 1, or sometimes you might see, maybe I think they might use r sub 1 here. Let me use r. So no, it is a. Sorry about that. A sub 1, it's the first term. Sometimes T sub 1, different letters we use. A sub 2, B sub 2. Sorry, that's not making sense. A sub 3, A sub 4, you get the idea. So it just lets you know that this is the first, second, third, fourth, and fifth term. That's all that's happening there. So a geometric sequence is one that has that quality. It always has what we call a common ratio. The common ratio is the value that I multiply the first term by in each subsequent term. So in this case, the common ratio, let me highlight it here, the common ratio was 1/2. In this situation, I didn't write it down, but the common ratio was -3. It was the thing that we multiplied each term by. The geometric sequence, of course, is this whole thing. Oh, I don't want that one. Is this whole thing here. This is the geometric sequence. It goes on forever and ever. And just to kind of organize our notes a little bit. And finally, this idea of geometric means. So if I were to give you a geometric sequence, let's say 2 blank, I'm thinking 4, and then 4 times 2 is 8, and then 8 times 2 is 16. If I were to give you a geometric sequence and give you a couple of values on either side, letting you know what the terms are, this is a sub 4, the geometric means would be the values that are in between, okay? So that's what they're referring to it here. We refer to it slightly differently in geometry, but no worries about that for right now. So that's what the geometric mean is, and we'll talk about different ways to find those values in between. So that's what's going on. I guess the value would be like 4 and 8 until we found the geometric mean in that situation. All right, so with that, let's go ahead and recognize whether we have a geometric sequence. So you remember, in a way, it's like if I had the first term a sub 1, the next term a sub 2 is going to be some r value. It'll be like a sub 1 times r. And the next term, a sub 3, remember we constantly multiply that by that common ratio. It will be a sub 1 times r, right? So r to the second power, because we constantly multiplying by the same value. And by that logic, we can deduce that to find a sub 4, we will be multiplying the first term or even the third term. We could think about a sub 3 times r, but it's really the first term, a sub 1 times r times yet an r again, so r to the third power. I'm hoping that makes sense to you. So we need to see this situation. Now, how can you determine if that's in one of these sequences that we get? Well, what you'll realize, it's called the common ratio for a reason. If I take the third term and I put it over the second term, you're going to get r as the value. Let's go ahead and take a look. A sub 1 ar to the second power over a sub 1 ar to the first power. Boom, boom. The r's cancel out and I'm left with just r. So when you are if you're dealing with a geometric series and you are dealing with numbers that are consecutive, if you put one over the other, you're going to get a situation where you get a common difference, all right? And so that's what we need to check out. And so when I put the 5 over the 0, I get an undefined statement. Already that's letting me know that the situation is not at all going to be a geometric sequence. And then 10 over 5 is not equal to 15 over 10. And so since that's not consistent, I know I don't have a geometric sequence, all right? So this is not a geometric sequence. In fact, this is an arithmetic sequence because we're starting with a number and we're consistently having what we call a common difference, not a common ratio, if you remember that from chapter 4. So let's check this one out. Again, we're going to take each consecutive value and we're going to make a ratio out of it. So I can take these guys and do 5 over 1. And that's 5. And then let me take these next two and try that, 25 over 5, and I got 5. Cool. And then 125 over 25, I get 5. Yes, this is a geometric sequence. They didn't ask us this, but this is a geometric sequence with a common difference, with a common ratio, rather, of a geometric ratio of 5. Shh, babies. Thank you. With a geometric ratio of 5. Okay, so here in example 2, what we realize is that we have a geometric sequence and we're asked to continue that geometric sequence. And so the way to continue a geometric sequence is basically to observe the pattern and continue. All right, but since we know that this is a geometric sequence, we know that we can find a common difference, common ratio rather, that's going to let us, not just observe the pattern and continue, but literally calculate the next value. And how do we do that? So what we do is we look at the situation by taking a pair of consecutive values. You take the one to the right of the other and you put the right one over the left one. I don't know why this is sounding very cumbersome, but you do what I'm doing here and you find out that the common ratio is -2. We could have also done it with 16 over -8 and we get a -2. Make sense? So now I'm going to use this -2, the common ratio, to propel me forward. So my next 3 values, let me go ahead and write this out like this. My next 3 values will be, my kids refuse to be quiet when I'm making videos. Like, they refuse. They're like, we're going to be the loudest. Okay, love them. So 16 times a -2 is a -32. -32 times -2 is going to be a +64. 64 times -2 is a -128. Didn't make sense? And so we got our next 3 terms, and we're going to do the same thing again. We're going to take our consecutive values. Notice I avoided that decimal because I didn't feel like playing that game. So I take 72 over 60. And the reason why I can avoid that fraction is because I know that it's a common ratio. It's going to be the same throughout. So 72 over 60 can be reduced by dividing top and bottom by 12 to 6 over 5. So 6/5 is the common ratio, all right? And so what I do is I'm going to multiply each each next term by 6/5. Oh, I can't avoid the fraction that long, right? Because the decimal, I've got 86.4 times 6/5. And so when I do that, okay, so I took the liberty of doing some calculations behind the scenes. When I multiplied these two values together, I got 103.68. And then realizing that 6/5 is really just 1.2, I multiplied this value by 1.2. I got this, and then I multiplied this value by 1.2 and got this, all with the help of Desmos. And so our next couple of values would be 103.68, 124.416, and finally 149.292. And so we're going to skip over a little example and just talk about this concept summary. And we kind of alluded to this before, but the nth term, if you want to find nth term, 5th, 6th, 7th, 8th, the nth term of a geometric sequence, and we'll call that a sub n, you need to know the first term. You also need to know the common ratio, the common ratio we talked about, and you would find to get to the nth term, you would multiply the common ratio n minus 1 times, which makes a certain kind of sense if we think about a sub 1, a sub 2, a sub 3, a sub 4, where r is the common ratio. A sub 1 is just itself. A sub 2, right, is going to be a sub 1 times the common ratio to the first power. A sub 3 is going to be the initial term times the common ratio again, meaning the common ratio to the second power. And then we see that pattern kind of continue. So it makes sense that to find the nth term, we'll do the initial term a sub 1 times r to the n minus 1 power, not to the n power. Okay, and so now let's get to this example here. We're going to find the nth term of a geometric sequence given some information. Find the sixth term of the geometric sequence where a sub 1 is 3 and r, the common ratio, is negative 5. Well, to find the sixth term, I'm looking for a sub 6. Remember our rule just now? It was a sub n is equal to a sub 1 times r to the n minus 1 power. It's a nice little tight formula, pretty easy to remember. So to find, let me give myself some room, a sub 6, I'm just going to plug in the information that I need to do. A sub 6 is going to be a sub 1 times r to the n minus 1, or r to the 5th power. A sub 6 is equal to 3 times negative 5 to the 5th power. And negative 5 to the 5th power. So with some quick calculation over here, we get a negative 3,125 when I raise negative 5 to the 5th power. And then when I multiply that by 3, our answer would be negative 9,375. So that's how quickly geometric series can kind of burst and kind of grow. And you might see why I related geometric series to exponential functions, because really in a lot of ways it is an exponential function. So you can kind of see that relationship. Let's see. So looking for the geometric mean, we need to find the geometric mean of the sequence. So we can look at this, and this is a sub 1, and this is a sub 2 that we're looking for, and this is a sub 3. So we're going to use kind of the understanding that we have of the relationship between all these values in order to find a sub 2. We know, like if I were looking for a sub 3, from that formula we talked about, we do a sub 1 times r to the second power, to the n minus 1 power. So and the reason why I'm choosing to use these two terms is because we have them. I know that a sub 1 is 2. A sub 1 is 2 and a sub 3 is 18. So when I replace them in my equation, 18 is equal to 2 times r to the second power. I'm going to divide both sides by 2, and I get r squared is equal to 9. And that lets you know definitely that the ratio, the common ratio that we're dealing with, is going to be most likely just 3, right? Not negative 3. Well, I guess it could be negative 3. That's an interesting one. Because if it were, let's see if it will work out. So let's say, I'm going to say plus or minus 3. I was going to get rid of the negative and be like, it can't be negative. But let's see, 2 times positive 3 is going to give me 6. And then 6 times that positive 3 gives me 18. That works. 2 times a negative 3 gives me negative 6, and negative 6 times a negative 3 gives me 18. Actually, both of these works. So I'm going to say that a sub 2 can be either 6 or -6. So I think the text just wanted us to go with 6, but I think we want to talk about both of them. So if you were to put both answers down, that would be most correct. All right, with that in mind, I'm going to let you guys go. Let me know if you have some questions, and I look forward to seeing you / talking to you really, really soon. Bye-bye.